Thank y'all very much. This is by far my new favorite conference. I love coming here and being able to nerd out with everyone about AI stuff, especially in the realm of cybersecurity and incident response and forensics. It's truly great to be here. We're going to be talking to you today about how you can take all sorts of cool machine learning, AI stuff, and apply it to how you approach your forensic investigations. We're talking about how you use LLMs, embeddings, and similarity to assist in your investigations. So I'm not Webster. What is similarity? I think we all kind of know what similarity is. The closeness between the likeness, resemblance between two or more things. But it's not something like we really think about a lot. But I think as we go through this talk, you're going to be like, oh yeah, that we can use similarity to do a lot of really cool things. In our investigations, a lot of times we ask questions that have to do with similarity. Some other ways we can use this in our investigations is how we sort data, or how to even quickly identify risky activity with a systematic process. So we're going to look at these things. How many times have you been doing a forensic investigation or incident response or some, maybe you're doing some threat hunting and he's like, hey, I found some activity, and it sparks more questions in your head. One of those questions might be, does similar activity exist? And then it's like, well, how early do we see that type of activity, right? And so these are all ways that we can use similarity to help answer those questions. What about sorting similarity, sorting by similarity? So kind of one of the things we're going to talk about today is how we can say, hey, let's look at commands executed on a system and how can we do stuff with those. So sometimes when you sort data lexically, we think A to Z, right? Maybe there's data in between on how we want to view it, where it sits in that sort order because of things like quotation marks, or in the realm of command execution, you maybe command.exe, maybe PowerShell is calling some type of activity. And so when you sort lexically, you don't see all of that grouped together. So here's an example where you have cluster data, which is like, similar commands being executed on this system. And you see a difference of when I view this lexically, I see it one way. When I view it by similarity, I see all of the stuff I would expect to be grouped together. It's kind of a cool way of looking at data. So what about finding risk? Like, what if I said, hey, out of all of the commands executed on a system, like, tell me about the different types of activity I have within that, right? So you could use similarity to group your actions based off of command execution. And this is kind of what we're going to be showing you today. So the question is, what do you get out of this? Because, if you come to this talk and you don't take anything away that you can go apply to your day-to-day job, it's useless, right? And so one of the things I want you to have is a way to kind of follow along. Now, you don't have to follow along live, like, we're talking about this, you don't have to run code or whatever, but I want you to take it back with you, and I want you to come back to what we're talking about today, and I want you to play with it. And so you're gonna get a Jupyter Notebook out of this. For those of you that are very technical and like to code and play with these things hands-on, this is great for you because you're going to be able to tweak these things and see how it works for you. There's also a Rust tool out there. I love Rust. It's one of my favorite things to program in. And so you're going to get a tool that allows you to run this on EVTX files on your Windows event logs and kind of get a type of output that you're going to see here in a second. So it never hurts to have another tool in your tool chest. I think we can all agree, there's just so many tools out there in this industry, and we all love tools. Tools are great, right? It allows us to play with data, to play with how we go about analyzing things. And so this is just another tool that you can throw into that tool chest. The benefit of this is it gives us a new way to explore our data. A lot of what we're doing and what we're talking about here is called data exploration. And we don't always have something to go off of when we're looking for attacker activity. We're just exploring the types of data, we're coming up with questions, and we're trying to find data points to latch onto to help us out in our investigations. So there's two phases of what we're going to cover here today. There's the phase one is kind of where we handle our data, and then the phase two is what I like to call doing cool things. And what we're going to do is we're going to take a look at how you can use embeddings and clustering and how you can use those things to help overcome limits of LLMs and how you can identify risk within commands executed. But again, while we're talking about commands executed, the technique you're learning here today is going to transcend to whatever is applicable to you. This is really cool stuff. All right, so we're gonna kind of walk through this together in a Jupyter Notebook. And I want to start off with a disclaimer because you're going to hear a lot of people talking today about the privacy, about the governance of how organizations are adopting AI. And so this goes into that, right? Everything that we're doing in this demo is using live data sets. It's public data sets, and we're using OpenAI to generate these embeddings. But you have to think about this when you go back and apply it to your everyday job of, hey, maybe I can't use those services because I can't take the data I'm working with and just send it out the door. And who knows how OpenAI is handling that data, right? There's ways to overcome that, and there's great talks today on how you can think about ways to overcome that issue, but it's worth stating as a disclaimer here that everything we do today, and when you go home and play with these notebooks, just realize they're set up to use open source data, they're using it against public APIs, so you have to be careful with that. So we're gonna start off in our phase one, prepping the data phase. I'm gonna hand it over to Dev, and she's going to talk to you a little bit about the basic of something called ETL.
Awesome, thank you, Matt. So essentially, ETL is the process of preparing our data for analysis. So the E here stands for extract, so we're gathering our data from all the different data sources that we'll be using. The T stands for transform, so we're cleaning our data to make it more structured and useful to us. And then the L stands for load, so we're storing our data for analysis later on. In our case, it's kind of just taking everything and plopping it into a data frame.
So like ETL, we actually use this all the time. We don't think about it as ETL, but especially if you're coming in from the approach of like the DFIR side, the digital forensics incident response side, right? All the time. Think about your MFT parser, your event logs. You're taking tools and you're extracting you're extracting data from binary formats. You're transforming that data. You're putting context to that data. Then you're loading that data into a CSV file or an Excel file, right? Think about Zimmerman's tools. You parse binary artifacts, you get CSV output. That's ETL. Extracting the data, transforming it into a human readable format, and loading it into another medium, EVTX, into a CSV or a text file, whatever, right? We do it all the time. It's nothing new. So in our Jupyter Notebook, when you go home and you replay this because you want to learn how to do all of those things, what we're doing is we're just basically doing that. We're defining, hey, here's a couple of columns I want to extract out of event logs. Remember, event logs can have like 5,000 unique attributes at any given time. Like if you were to iterate over all your event logs, just absolutely crazy. So we have to normalize it. So here's our ETL process in that Jupyter Notebooks. You just define a transformer, you say, hey, here's some columns, here's the attributes from the event logs that are going to represent the values of those columns. And in the end, that's what we want to do. So in this case, we want to get a list of all of our command lines being executed on the system. So now that we have our our data in a couple columns, we're going to do stuff with that, which brings us into the phase 2 of doing cool things. And now Dev's going to talk to us about what embeddings are, because that's the next step of this.
Awesome. Thank you, Matt. So essentially, embeddings are a way of representing text numerically. And the reason we have to do this is because machines can't just process text. We first have to convert the text into a format that the machine can understand, so numbers. So let's go ahead and take a look at an example here. So let's say we have the sentence, "I think embedding is so cool," which it is, and you're about to find out. Our first step is to divide this sentence up into these chunks called tokens. So tokens can be words or part of a word or even multiple words, depending on what embedding model we're using. In our case, we just have tokens for each of the words in our sentence here. Now that we have our tokens, the next step is to generate vectors for each of these tokens. So these vectors are generated by embedding models that do this by analyzing vast amounts of text and kind of identifying patterns in the way that words are used. And so each number in these vectors represents a dimension, which captures some aspect of the word's meaning. And oftentimes these vectors can be really, really, really big. So the vectors here are generated through the word2vec model, and each of these vectors have 300 dimensions to them, which is a lot of dimensions. And if we think about it, it's really difficult for us to visualize what 300 dimensions might look like, right? So we'll actually talk a little bit more about this later on and techniques that we can use to help us visualize this high dimensional data. But for now, maybe we can use a more hypothetical example. So here we have the embeddings of the words kitten, cat, puppy, and dog. And that's actually a picture of my dog that I've added just for fun. The idea here is that words that are similar in nature will be grouped closer together to reflect this similarity. So we can see that kitten and cat are on one side, puppy and dog are on the other side. In this example, we would also expect that the distance between the embeddings of kitten and cat would be very similar to the distance between the embeddings of puppy and dog, because kittens and puppies, they're just younger versions of cats and dogs. So we would expect that their embeddings would reflect this similarity as well.
Yeah, so I bet at this point you're like, whoa, but how does this play a part into my investigation? Well, let me show you. This is where things start to get cool. Remember, we're in the do cool things phase now. So again, a snippet of the Jupyter Notebook. When you go back and you're going to apply this because you want to learn these concepts, this is where we start generating those embeddings. So on one side here, we have a command line executions. On the other side, we have their embedding vectors. So it's just the vector of a huge list of numbers, and that list of numbers represents that command line. So these vectors can get huge. So we talked about large dimensions. Dev was just talking about 300 dimensions using one technique. With OpenAI, this is what the default dimensions could be. It's thousands of numbers, right? So all of these numbers represent one command line that was executed on this system, right? But that's okay. You don't need to know. You don't need to know anything about these numbers right now.
Okay, so onto the fun part, clustering. So before we get into clustering, let's maybe think about machine learning as a whole. So very broadly, we can categorize machine learning into two types. So we have supervised learning and unsupervised learning. The main difference between these two is that supervised learning uses labeled data, unsupervised learning uses unlabeled data. And labeled data is just data that has a known answer tag to it. So an example of this is spam classification. So when we want to classify emails as spam, the email is either spam or not spam. There's really no other answer here. With unsupervised learning and unlabeled data, this is maybe not so straightforward. So an example of this is Netflix recommendations. So when Netflix gives us recommendations, it does this by grouping us together with users that have similar viewing patterns. So if we think about it, there's really no right or wrong answer here for user preferences. So the two main techniques with supervised learning are regression and classification. We really won't be going too much into detail on those two. With unsupervised learning, our main technique here is clustering. And because in our case, because we have unlabeled data and our goal is to group together similar commands, we performed unsupervised learning through clustering. Okay, so there are a lot of different ways we can go about clustering. So the method that we chose is called DBSCAN, which stands for Density-Based Spatial Clustering of Applications with Noise. Essentially what it does is it clusters based off of density. And we can kind of see this in action here through this GIF. It's pretty long, so we won't be able to see the whole thing. But we can also compare this with another very popular clustering technique called K-means. And so the outputs on the right are the outputs of the K-means and DBSCAN clustering techniques on the same data set. And we can see that even though it's the same data set, the outputs are completely different. And this is because inherently, K-means and DBSCAN are very different clustering techniques. And so I've outlined some of those differences in the table to the left here. So one of the biggest differences is that with K-means, we have to define our number of clusters, or our K value. So in the K-means output, we can see that there are 4 clusters, which means that we must have defined our number of clusters as 4 to produce these 4 clusters. With DBSCAN, you don't have to do this. It automatically finds the number of clusters for you. Also with the K-means output, it looks like our clusters are able to be almost divided by these like straight diagonal lines, right? So this is called linear separability, and this will always be a result of K-means clustering. With DBSCAN, this is not necessarily the case. And then lastly, let's just say that we have a data point that's just way out there. With K-means clustering, this data point would have to be tagged to a cluster. Whereas with DBSCAN, it could be tagged to a cluster, or it could be tagged as just noise. So those are a couple differences there. So we looked at a couple different ways we can go about clustering. The main takeaway here is that there's really no right or wrong answer. So depending on your goals, depending on your data set, some techniques might work better than others. So it's up to you to experiment with your data and kind of see what works best.
Yeah, so remember, and it's very important to remember that key is like, there is no right or wrong answer here, which is really cool and gives you a lot of liberty in how you play with these things to see what works best with you. A lot of us, sometimes we go into a new skill or technology and we're scared to use it wrong, right? I think a lot of us have had that fear before, like, what if I do this wrong? It's like here, it's like there's going to be better ways of doing things. And maybe if you try to achieve one thing, it's better if you do this or better if you do that to do something else. So there's no right or wrong answer here, which is great. So again, here's some vectors. They represent our command lines. And then now we're going to pass this to the DBSCAN algorithm, okay? This is how cool these things are, is because in 2 lines of code, you can do some insane math that's about to show you something really cool. 2 lines of code. You don't have to know about how the DBSCAN algorithm works or the math behind it. That being said, if you do want to know about it, I highly recommend Sans Sec 595. It's a fantastic class. You take that class and you're like, they're gonna go over the math with you and you're like, this math is insane. But at the end of the day, you don't have to remember that math because you can do it in 2 lines of code. All right, so we took all of our command lines, we turned them, that got executed on a system, we turned them into these vectors of dimensions, and then we pass this to the DBSCAN algorithm. It says, hey, we found 119 clusters of all of your different types of commands. So if I were to say, hey, how many commands do I have? And like, let's say the cluster 0, there's 2 commands. In cluster 1, there's 36 commands. Now, again, one of the side effects of DBSCAN is that you have unclustered data, unlike K-means. So there's actually 286 commands that were executed on this system that weren't clustered at all. Remember, each one of these clusters represents commands that executed on a system that were similar to each other. And you're about to see what that works out to. Alternatively, if you wanted to use k-means clustering, you can do that as well, and we'll take a look at how you do that in code as well, because again, it's good to know how to do both methods because neither is right, neither is wrong. You're playing with this to understand these concepts and how they relate to you. So we can take scores. Remember how Dev said that when you use k-means, you have to know the number of clusters ahead of time. So there's kind of different techniques you can use to figure out that number. And so what we did is we can take silhouette scores, we iterate all of our commands, the vectors into the k-means algorithm, and we run a score on it. It's called a silhouette score on it to figure out how many clusters we might want to have. This one says, hey, 190 might be a good number of clusters to have on this data for using k-means. Remember, DBSCAN method only found 118 clusters. So there's a difference already out of the box there. So if you were to look at this, you could see something like, okay, using k-means, our cluster one has 152 command lines in it. Some of these only have one command in it. For example, cluster 186 only has one command in it. You wouldn't have that with DBSCAN because DBSCAN says, hey, depending on how you define it, I need at least two things that are similar to each other to put that into its own cluster. K-means doesn't care about that. But now let's see how this affects you. All right, so we have these list of commands that executed on a system. We then created embeddings for those commands. Then we clustered those embeddings. How does that affect you? Well, if I were to say, hey, what commands do I have in, like, let's say cluster 79? You can see here a whole list of winponage that ran on this system, and they're all grouped together. Now, notice these values aren't the exact same thing. It's just saying that, hey, all of these commands are similar to each other. Now, how are they similar to each other? That's the part where you can improve this process. Is like you could do different things and define how you want that similarity to be based. But by the essence of the command itself and running embeddings on it, it's being grouped like this. And this is actually really good. So if I were to say, hey, we know the threat actor was using winponage, what all did they do with winponage? Now I can look at this group and instantly see, here's at least some of the things they were doing with winponage that were kind of similar to each other. That's a great start to understand the type of activity being used with a tool, right?
All right, so now we're on to the visualization piece. So we're able to visualize with the help of what's known as PCA. So PCA stands for Principal Component Analysis. Essentially what it does is it helps us simplify very complex and high dimensional data while still keeping those important patterns from our data set. So let's think about it this way. Let's say that we have a tennis racket in our hand. So you have the head of the tennis racket, you have the strings running back and forth. We also have the handle of the tennis racket, right? With our hand, we can also move this tennis racket around. So it's a three-dimensional object that exists in a three-dimensional space. Now let's say we take a light and we shine it onto this tennis racket and it casts a shadow onto the wall. Essentially what we've done is we've taken this three-dimensional object that exists in a three-dimensional space and compressed it into an image of a three-dimensional object that exists in a two-dimensional space. And so this shadow of the racket, it doesn't tell you everything there is to know about the tennis racket. There is some information loss that happens here, but we can still tell that it's a shadow of a tennis racket. So very similarly, PCA helps us kind of simplify very high dimensional data, but still keep those important patterns from our data set. Okay, so let's revisit the example that we used in our embedding section. So if we remember, we had these really big vectors and they had 300 dimensions to them. And the problem that we face is that it's really difficult for us to visualize what 300 dimensions might look like. We're only used to visualizing things in 2D or 3D. So now with the help of PCA, we can take this high dimensional data, reduce the number of dimensions by keeping only the most important ones, and then use that to visualize our data. And just as a reminder, in case you forgot how gnarly our data looked back when we generated our embeddings, here's a picture of it. So it's really incredible that we can use a technique like PCA to make sense of something that looks like this.
Again, just to call out to how easy this is in Python, again, only you're doing some crazy complicated math in like 3 lines of code that's going to let us do something really crazy. So you see an example here, we transform thousands of dimensions into 3 dimensions. What can we do with 3 dimensions? Well, now we have an XYZ axis, right? So now if we were to plot all of that on a graph, what you see here is all of the command line execution on our system represented in a 3D graph. Now, how does this help you? It might not even really help you other than just say, hey, this is really cool stuff and give you a little, ooh, that's pretty, right? Because if we clicked on any one of these clusters, what's cool is this is cluster 30, right? It's kind of way out there by itself. All of cluster 30 has a whole bunch of SVC host execution, right? And so this is a really cool way as humans for us to understand visually what it is we're trying to accomplish here, which is take command line execution and group it into similarity. And we're about to show you why that's really important. So now we're going to move on to the final step in our doing cool things phase, which is where we're going to start adding in LLMs to the mix. Now, if you're like me and you have people that are like, hey, how can we start using AI in our investigations? And you're just like, dude, this forensic image, this data set, my sim has terabytes of data in it. I don't know how I can do that. If I tried and copied and pasted this timeline or whatever into GPT-4 or whatever, you're going to quickly find out that's not possible. It's too much data. You're going to run into limitations. So then it gets us thinking, like, how do we overcome the limitations of our LLMs, right? And this is a great way of doing it. It's because really what we're talking about here is we're talking about breaking large groups of data into bite-sized chunks. What we're saying is out of all of the executions on this system, out of all of the web history, out of whatever it is, we're taking large chunks of data and we're saying we're going to break it into small chunks that are similar, have similar data in it, and then we can work with those small pieces individually. So if you're a big fan of Art of War, right? This is one of those core principles. You take the whole army, you break it up into bite-sized chunks and attack each chunk, right? So we're gonna do the same strategy with our forensic data using Similarity, and now what we have is clusters of similar executed commands. So what we're going to do is we're going to iterate each cluster of commands executed. We're going to take a sample of that and we're going to pass it to our LLM, right? And so we could say something like, hey, for each cluster, here's data that represents what's in this cluster. Give me a risk associated with it. Give me a description of what type of things I'm going to find in this cluster. And then we can iterate that across the whole. So we just took something where we might find tens of thousands of executed commands on a system. We turned it into maybe 200 smaller groups of things to do something with it. Our LLM can handle that. So that was our prompt. Next. This is in the code where we iterate each of those clusters. So if you want to follow along on your own, this is where that happens. And in the end, what we're going to end up with is an output of saying, hey, in this cluster of commands executed, here's a description and here's a risk associated with it. So if we go back to our cluster number 79, like we were showing earlier, when ponage usage, we get a description saying that, hey, commands executed using when ponage to manipulate whatever. Our risk score associated with that is 9. You should probably look at those commands. Like those are probably important. Of course, As analysts, we want a workbook to work with. We want good output. So we throw all of that into an Excel workbook. This is what that's going to look like. You basically end up with this output of, hey, here's all of our clusters. Here's their descriptions. Here's their risk scores. Then the next thing you can do is you can go and look at any one of those cluster numbers and you can see all of the commands associated with that cluster. So that's really cool. So going back to the whole data exploration thing, this just gives you another way to quickly run through all of those commands executed on a system and see where they fit. There's a Rust tool. I apologize, it's a little broken. I'm going to skip this part. You can go follow the GitHub. I'll fix it here shortly. But what's next real quick? We've basically almost created a RAG tool at this point. We have all of the embeddings for all of our executed commands. You could turn this into a RAG system really easy. Just as much, another cool concept I like to think of, what about IOCs? IOCs have traditionally always been a very specific value. What if we had vectors that represented bad activity? And in my environment, I said, hey, do we have any known activity that's very similar to known bad activity? That would be kind of cool, right? So it's just this idea that I think about, like, what if we had vector type IOCs? It would be interesting. All right, and then of course, give a quick thanks to some of the libraries and tools that we're using for these open source stuff. And then of course, my favorite SANS class, Security 595. Absolutely great class, one of my all-time favorites, led to this content. Yeah, and thank you very much. We'll go into some Q&A real quick. If any of y'all have questions, you can follow me and Dev on LinkedIn.
Thank you.